Good morning, everyone. My name is Carlos Fernandez Moro. I am a pathologist at Karolinska University Hospital. It is a great pleasure to participate in this online format Sugosuet and be with you. And I would like to start by thanking the organizers for making it happen despite the difficult COVID times. In the next minute, I will be describing and sharing with you some of the experiences on AI and mixed reality projects for digital pathology at Karolinska University Laboratory. In order to give a comprehensive view of them, I would like to touch not only the purely DigiPath results, but also the different related aspects that are relevant for their development, like the environment for research and innovation, clinical diagnostic context, the model of project development, and some details on the way AI deep learning algorithms work. Most of these DigiPath AI and mixed reality projects are developed as research and innovation projects, two crucial dimensions of our work, and I could say duty, as pathologists in general and university hospital in particular, to actively contribute and shape, according to our knowledge and needs, advances and improvements in the new camp era of digital diagnosis. Clinical pathology is a diagnostic medical specialty that has become decisive for oncological care. It is undergoing a progressive subspecialization in diagnostic areas with adoption of advanced diagnostic methods. Still, clinical pathology is only partly automated and mostly on the laboratory side. The results we generate must be reproducible and evidence-based, which requires robust quality assurance and standardization. And cancer registers must be supplied with accurate data that is employed among other uses for research and public health planning. The workload in pathology is increasing steadily, due in part to a higher complexity of the diagnostic proofs. And we perform a high proportion of human-based medical decisions where support, including from AI, is needed. Very briefly, the function area of clinical pathology and cytology at Karolinska comprises 4 sites and 5 function units with 430 employees and a production of 300,000 cases per year. It is nationally accredited, both as laboratory and in 5 diagnostic areas. Digitalization is ongoing, with increasing number of pathologists being validated for digital diagnosis. And the area is involved in several AI and innovative projects in digitalization. Besides our own pathology expertise and resources, we count with the support from Karolinska Innovation Office in Avahunsplatsen, as well as the important coordinative, operative, legal, IT, and administrative support from Karolinska University Laboratories to carry out the innovation projects and the development projects. And within the own department, there is also a dedicated section for research and biobank, close relation and communication with the clinicians in all the subspecialties, our residents who are encouraged to participate in the innovation projects on a flexible basis, representation in most national boards within healthcare, and international collaborative partners, especially Semmelweis University Hospital in Budapest. clinical pathology changes rapidly from analog microscopy to digital and computational pathology. This process should be considered not only as a purely digital exchange of the classic microscope, but rather opens a whole new range of possibilities for visualizations and analysis of images. The ultimate goals of the digitalization process are helping doctors to do diagnosis better, to provide improved value-based patient care, while at the same time optimizing the laboratory processes. But first, we may ask ourselves, do we need to traverse this technological path? Does it really add value to the pathology profession? We think so, because not only cancer projections are growing, which translates into increasing number of proofs, but very especially surgical techniques and oncological treatments are improving steadily in the quest for a more personalized medicine, and this translates into increasing complexity and reporting requirements of pathology proofs. On the other hand, there is a general shortage of pathologists worldwide, so digital diagnostic tools are our best chance to cope with the increasing demands. From a technological point of view, the current state-of-the-art AI deep learning algorithms can now match and even compete with human experts in natural image classification, including the medical field. The implementation of AI diagnostic support tools enables unrivaled capabilities for qualitative image analysis, as for automatic tumor detection, and quantitative image analysis to fulfill the need for computational pathology. So the first project I would like to present is an AI diagnostic support tool for automatic tumor detection in primary colorectal cancer and lymph node metastasis. Colorectal cancer is very briefly a malignancy that starts in the colon of the rectum, and most of these cancers are composed of malignant glandular epithelium, what we in pathology call adenocarcinoma. Colorectal cancer is the third most commonly occurring cancer in women and men together, with over 1.8 million new cases worldwide in 2018. And is also the second most common cause of cancer-related death worldwide. The 5-year survival is about 65%, where mortality is mostly due to the occurrence of distant metastases, mainly in the liver or lung during the course of the disease. But colorectal cancer is, as many other cancer forms, far from being a uniform disease. Rather, the individual patient's treatment and prognostic stratification are highly determined by tumor stage. In particular, stage 3 is when the cancer has already spread to the lymph nodes. The pathological diagnosis in colorectal cancer is then determinant for an accurate tumor staging, for further management of the patient. In particular, lymph node metastasis is a crucial factor to decide the use of adjuvant chemotherapy after surgical resection, and to provide the multidisciplinary team conference with important feedback information. This slide summarizes the standard pathology workflow from the formalin-fixed surgical specimen to the slide preparation in colorectal cancer. As you well know, it involves a high amount of thorough manual work and yields about 40 to over 100 histological slides per proof. Finally, to fulfill the clinical requirements, the pathologist must report as a minimum the parameters in this structure report. accurately and fast. So we may have some problems. Mainly, time and resource-intensive workloads due to high numbers of large and complex proofs. A high diagnostic accuracy is mandatory to treat patients correctly. Overlooking regions of cancer may lead to understaging and possibly undertreatment of patients. Short turnaround times and a shortage of pathologists subspecialized in gastrointestinal pathology worldwide. AI-based diagnostic tools can then support and enhance us pathologists by optimizing the workloads. We pathologists dedicate a high amount of work to screen and eyeball the numerous slides searching for cancer cells. This repetitive, time and resource consuming task can be significantly streamlined by the AI. Securing or contributing to secure the diagnostic accuracy by graphically signaling the cancer regions and shortening turnaround times. Automatic tumor detection may significantly reduce the pathologist's time needed for a complete and thorough case review. So, to start addressing these challenges, we initiated this project aimed at creating an AI-based diagnostic support tool for automatic tumor detection in colorectal cancer. The main steps in this kind of project are, first, the creation of a large multi-class repository of pathology annotations, so-called ground truth. Then, training of AI models with them. And finally, evaluation of AI model performance for automatic tumor detection. This project is a fruitful collaboration with Semmelweis University Hospital in Budapest as clinical partner and builds upon a previous research and development pre-study done in collaboration with SAP and Queen Mary University of London as industry and academic collaborators. How was this done? First, our pathologists annotated manually the different cell types and tissue components in digital histological slides of primary colorectal cancer and lymph node metastases, according, as we can see in the image to the right, to a comprehensive and flexible multi-class annotation scheme. The main requirements for the annotation task are to capture both the intra and inter-slide morphological variation for the different classes, and to ensure a high accuracy of the pathology annotations in order to train and evaluate the models correctly. In the example in the image, we can see very highly accurate manual annotations in red for the colorectal cancer cells, in light blue for a germinal center that are morphologically somehow different from the more compact lymphocytes in dark blue, and even a small annotation for the endothelial cells that when activated, they can even morphologically mimic some tumor cells. So it is important to annotate as rich and comprehensively of both all the different cell types and cell types and tissue components, and also the different appearances within the slides and between slides. And here we can see also, but not also, the tumor is embedded in a tissue environment, histological environment. So here we can see also further examples of annotations for the intestinal wall, the muscularis propria in green, and also the surrounding soft tissues. The current dataset is composed of 600 whole slide images scanned at 40x magnification, containing over 70,000 high-quality manual pathology annotations. Of them, over 40,000 from colorectal cancer cells in their different morphologies, appearances, histological variants, differentiation grades, etc. And here we can see an example of the preliminary results. Up to the left is a digital histological slide, hematoselinous staining of a lymph node from a colorectal cancer proof. And next to it, we can see in red overlay the AI-based automatic tumor detection. The AI can detect and highlight accurately not only larger tumor regions, but also individual tumor glands. And to the right, to the most right, even a single layer of tumor cells. Cross-validation when grouping the cancer-related classes or labels versus the normal ones resulted in both a sensitivity and a specificity over 99%. These results highlight both the potential of AI-based diagnostic support tools for pathology and also the value and suitability of our dataset of images and pathology annotations for AI development. Our next steps are to identify and select an optimal industry partner through public procurement for the co-development of an advanced AI diagnostic support tool for automatic tumor detection in hematoselinous slides of colorectal cancer. Afterwards come clinical validation, CE marking for clinical use, and our more pursued objective, implementation and integration of the AI tool within the digital clinical diagnostic workflow. Afterwards, cycles of improvement, upgrade of the AI tool based on feedback loop from pathologists need to be planned and carried out, for example, to address eventual misclassified regions, new tissue morphologies, and so on. To create a diagnostic support tool that is to be implemented in the clinic, as I mentioned before, our aim is not just a research project, but to a real clinical implementation and broad adoption. To create such a diagnostic support tool that is to be broadly implemented in the clinic, it is crucial to consider carefully the different possible and alternative project tracks. This can be summarized as own development or a research collaboration, Fous and Berkan, co-development, or simply buy of an already existing product in the market. Each of the tracks has its advantages and limitations, but in the end, concurrence setting will be required upon involvement of an industry partner for a real-world implementation. An interesting track for a healthcare provider may be co-development with an optimal concurrence with such industry partner. In this concept, each party benefits from the process and product, and also carries out its own cost. For example, healthcare may contribute with a clinical need, clinical resources, data, clinical infrastructure, and clinical validation. And in return, benefit from, for example, a royalty-free license to the product, improvement in patient care, and organization efficiency. While the industry partner may contribute with AI and IT expertise, product development, and CE marking, and benefit from product intellectual property rights and worldwide commercialization. The second project is an AI-based diagnostic support tool for, in this case, the previous use case was a qualitative image analysis, we can say, but in this case for quantitative analysis of colorectal liver metastasis. Surgical resection, usually after perioperative chemotherapy, is the only treatment associated with a long-term survival for patients with colorectal liver metastasis. After the operation, the pathologist assesses a number of clinically relevant parameters, among them the grade of response to the perioperative chemotherapy according to the percentage of residual tumor cells, and the so-called histological growth patterns, mainly replacement and desmoplastic at the tumor border, also called at the invasion front. The project outline from a technical perspective is similar as previously described, and this is a fruitful collaboration with the Multimedia and Vision Research Group at Queen Mary University of London and Marco Gerlin's research group at Karolinska Institute. Just a brief note about the histological growth patterns in colorectal liver metastasis. In the replacement pattern, the tumor cells establish direct contact with the surrounding hepatocytes and progress along the hepatic trabecules, replacing them. This growth pattern is associated with a poorer overall survival. While the desmoplastic pattern to the right, in this pattern, a rim or a pseudocapsule of fibrotic tissue separates the tumor cells from the surrounding hepatocytes, and this growth pattern is associated with a better survival. But there is a catch. As usual in pathology, both growth patterns can occur in the same metastasis, and often do, which difficult their quantitative assessment. We humans, we pathologists, we are very good for qualitative assessments, but not as good for reliable, reproducible, and comparable quantitative assessments. As in the previous project, first our pathologists annotated the different cell types and tissue components in whole slide images of resected colorectal liver metastasis. In this example, we can see examples of annotations for tumor in red, necrosis, necropoptotic, proptosis in yellow, and fibrosis in green. The current dataset is composed of 75 whole slide images containing over 17,000 manual pathology annotations. These are being used to train and validate the AI models. What happens next is rather interesting, and it may be important for us pathologists to have a basic understanding, as it may help us understand why an AI may generate what we might consider strange results and envisage ways of improvement. So, to begin with, our annotations are not used as drawn by us by the computer algorithms. Rather, the pathology annotations are cropped by our dear AI experts into many labeled square patches of fixed size and magnification, as in these examples. They are called image patches. These patches of fixed size and magnifications are the basic image units, we can call them, that the algorithms will be working with. We have heard that training good deep learning AIs require very large amount of data. At the same time, there is the risk of so-called overfitting. In the pathology case, when an AI performs well in new images coming from the same laboratories which provided images for training, but performs surprisingly poor when processing images from other labs which may have subtle differences in, for example, hematosylinios staining and scanning protocols. Put with another words, the AI model is not generalizable. To improve both for data amount and generalization, so-called data augmentation techniques are commonly applied, where different image transformations are applied to every tissue patch, generating multiple transformed versions of it, for example, with changes in color, brightness, and orientation at different degrees. The augmented collection of tissue patches is then used to train a deep learning so-called convolutional neural network. When training a neural network or any other type of machine learning model, what we are really doing is tuning its parameters such that it can map a particular input, let's say a patch from annotation in a pathology image, to some output, in our case, a tissue label or class, that like tumor, necrosis, mucin, and so on. Similarly, once trained, the neural network cannot process the whole pathology image. It is simply too big. Rather, it is divided into a large amount of also small tissue patches that are fed into the neural network as inputs, are processed within, and produce each, as a result, the predicted tissue label or class. That means some of the patches we see to the left will be predicted to be of hepatocyte label or class, others will be predicted to be of tumor, and so on and so forth. More precisely, for each small patch, the network can generate a probability for each of the tissue labels, for all of the classes, for each of the classes. Here we see a cropped regions in an image that will be divided into a large amount of small patches. And here we can see the probability maps of each patch to of being predicted or belonging to each of the classes of the tissue cell types and tissue components in the model. In this example, the image region in hematosylinios will be divided, as I said, in the small patches, and we can see the so-called heat maps indicate the probability high in red and low in blue of each patch, each small patch belonging to each tissue label. As we can see, the patches from the upper left part of the image have a high probability of corresponding to inflammatory cells, but low of corresponding to tumor. While in contrast, the patches from the lower part of the image have a high probability of corresponding to tumor, but low for inflammatory cells. In the next step, each small patch in the image, as we saw before, is classified in a unique way according to the label or to the class with highest probability among the ones we saw before. Accordingly, patches on the right side of the image were mostly classified based on the previous heat maps as inflammatory cells, while those on the bottom were classified as tumor. But we pathologists do not work with probability maps or with classified patches, strange things, but rather with areas with defined shapes and boundaries. So in a final step, the heat maps of highest probability in the previous slide for each, and here also to the bottom, for each tissue label are processed in a special way called image segmentation, generating as results spatially defined classification areas for each tissue label, as in the top right examples. These will be the tissue regions, the defined tissue regions with shape and boundaries for the tumor according to the predictions in these two image regions. And these segmentation results, these defined regions with boundaries, can finally be readily visualized as overlays or as polygons on top of the original image in a digital pathology viewer. We could think of them as AI-generated annotations. Now, coming back to the project, AI for quantitative analysis of colorectal liver metastases. Here is an example of the results in a new image that was not used for training. To the left is the original hematocilin eosin staining, and we can see to the right that the algorithms correctly classify and segment the different cell types and tissue components. Pink corresponds to the hepatocytes, brown to the tumor cells, gray fibrosis, blue mucin, and red necrosis. But more importantly, after segmentation, the algorithms can quantitate in a precise, objective, and reproducible way the clinically relevant parameters, that is, the percentage within the metastasis of the different tissue components, tumor for the assessment of the regression rate after preoperative chemotherapy, fibrosis, necrosis, etc., and the percentage along the tumor border, along the infection front of the histological growth patterns, replacement and desmoplastic. Some conclusions on AI for digital pathology. Clinical pathology is a crucial medical specialty for modern cancer diagnosis and care. There is an urgent need for automated, computational, and resource-optimizing AI-based diagnostic support tools. This will empower pathologists to make diagnosis better and more efficiently, and as a result, improve treatment for the patient. And a big thank you to all the persons whose awesome work and support make this AI project happen. The third and last project in this presentation is integrated radiology pathology diagnostics with support of HoloLens Microsoft mixed reality technology. As very briefly, as seen before, cancer diagnosis, both radiological and pathological, is the basis for high-quality cancer care. As mentioned before, a reliable diagnosis and staging of cancer are crucial for the patient's treatment and prognostic stratification. It is an important and difficult assessment that involves several specialties, in particular radiology and pathology, with its various image modalities. These are presented and discussed at the multidisciplinary team conference to determine the optimal treatment for the individual patient. Correlation of diagnostic findings between radiology and pathology is highly valuable as feedback information on the preoperative radiological diagnosis, assessment of the quality of the surgical procedure, and assessment on the effect of the preoperative treatment. A tool for spatial correlation of multiple image modalities of radiology and pathology is in great demand clinically, but to date still missing. How do we aim to meet this clinical need? First, by defining a standardized pipeline for imaging and alignment and registration of radiology and pathology image modalities, from 3D radiology, 2D radiology, 3D imaging of the surgical specimen, pathology, macroscopic tissue slices, histology, and from then also immunohistochemistry. And by developing a visualization app that integrates radiology and pathology image modalities for their simultaneous analysis and correlation. For this, we are exploring mixed reality technology as a potentially useful, versatile, and interactive environment. We can see to the left, to the right, two versions of the interactive versions of the current mixed reality app that is under development, where we can see examples of integrating radiology and pathology image modalities, both for pancreatic cancer and prostate cancer, where the different multiparametric MRIs and image modalities can be simultaneously synchronized and precisely matched between radiology and pathology. Here we can see the current status of development of the mixed reality app. In overview, the various display panels, like in an amphitheater layout, show from left to right radiology, pathology, macroscopic tissue slices, histology overview, histology viewers, and the clinical information. And the key of this application is that all the visualizations in the different display panels are synchronized. Integrated diagnostics may contribute to an improved radiology through better feedback from pathology, to an improved pathology through better knowledge of the preoperative radiological findings that, for example, motivated a certain extended resection, together to a more patient-centered, to a more holistic care. And through all this, to a better treatment for the patient. Why now? As said before, clinical pathology rapidly transforms from analog microscopy to digital pathology, and this opens up a whole spectrum of possibilities also for multimodal and even cross-specialties visualizations and analysis of images. While at international level, integrated radiology pathology diagnostics is a field of increasing interest with rapid developments in the field. The project counts on highly qualified expertise in the respective fields: radiology, pathology, mathematics and medical imaging, innovation management and consulting, and industry partners. And I heartily thank the entire team for the outstanding work and commitment. And finally, thank you everyone for your attention. Is there any questions or comments? I cannot see questions in the chat. No, sorry. Any questions? Or if you would like to share your views on or experiences also in this field. There are some questions. First, validation of digital pathology. Stefan, validation of digital pathology has been performed and published many times, including even in telepathology consultation setting. Is it necessary to validate digital pathology at Karolinska for all separate cancer areas? It's a very interesting question. I think it is, important that that pathologists validate within the area where one develops the most of the daily work. There is also a particularity probably in Karolinska, that is that we usually work quite intensively in a specialized context. So we work intensively in diagnostic groups. So it makes sense that when we implement the digital workflow in the clinic, we perform the validation also within the specific subspecialization diagnostic group, and that in such way the colleagues in the group we become also calibrated and can share experiences and tips and key hits regarding the digital diagnosis in the specific area. And this may be also may be quite different from area to area. Some diagnosis will have quite a lot of large specimens. Other areas will have, for example, more high amount of biopsies, different amounts of immunohistochemistry. So I think it is important or useful, can be of value to do the validation per diagnostic groups for subspecializations. Another question. Kan du beskriva dataset i ment och varifrån det kommer till projekt 1? Hur har ni resonerat kring hur man får använda data för samarbete kring produktutveckling har ni efterfrågat consent eller går in på etiktillstånd från forskningsperspektiv? Just of course. So all these projects are covered before inception from a detailed and very highly specified ethical permits. And because they are based on retrospective data, initially are fully anonymized and after an ethical amendment pseudonymized, and due to the long time from the diagnosis to the study and the in the long term poor prognosis of the disease, consent was not required from the ethical committee. But of course, everything has to be very clearly approved by the ethic provenance vindicating before a study starts. And the data set about the 650 whole slide images, about 2/3 of the images comes from Karolinska and about 1/3 of the images comes from Semmelweis University Hospital. And this is important because one of the problems with the images and the annotations is the so-called, as we said before, the overfitting. So in this data set, we count with 2 different hospitals, labs with different hematocylindosine techniques and different scanners. Karolinska, they are Hamamatsu, and in Semmelweis, they are Mirax. And we have also different, subtly different hematocylindosine staining. So this will contribute to increase the robustness and generalizability of the AI models. And also, there may be a factor that is the bias of pathology bias in how we do the annotations. And the annotations have been done for a large amount of pathologies, both from Karolinska and from Semmelweis. So let's say that we can minimize bias derived by, for example, a single or a small group of annotators. Yes, how many pathologies? So from Semmelweis specifically, there were like 17 colleagues, and from Karolinska also around 13, 14 pathologists, specialists, and residents doing the annotation task. Thank you. Yes, we have done proofreading. So after the initial annotation, there has been a senior pathologist in GI that has gone through all the images and annotations and proofread and corrected them. Thank you. Is there any other questions or comments? Thank you very much. It has been a great pleasure to be with you today. Thank you. I'm looking forward to fortsätta med en jättespännande vårmöte nästa föreläsningar. Ses där. Hej då.